Now that we've described a bunch of this stuff, let's talk about resource allocation and control in TiDB. One of the biggest challenges we face when planning to consolidate single-tenant databases into multi-tenant databases is how to ensure that the user experience of the various systems meets or exceeds expectations. It's important to remember that users will compare the old single-tenant environment to the new multi-tenant environment. They will be very disappointed if they notice a drop in performance. We know that disappointed users will complain about this nonstop. They won't care that the new system is more efficient and reduces cost. The diagram on the left shows a traditional single-tenant environment. Recall, this architecture makes optimizing the database easy because you tune the database for the one application running on it. On the right, we see a multi-tenant environment. Notice the box around the databases. This signifies that our individual database instances are consolidated and running in a multi-tenant environment. So in a multi-tenant environment, we must be able to tune computing power and storage for the many databases running in the box on the diagram. Traditional multi-tenant databases often view their computing power and storage as a large resource pool, or parent resource pool, which contains all CPU, memory, and I/O resources. Before consolidating data, we must create a corresponding sub-resource pool for each existing single-tenant system. For example, in the picture, the parent pool consists of 64 CPUs, 1,000 gigabytes of RAM, and 10 terabytes of storage space. Assume we must accommodate 3 databases, or tenants. We will call them DB1, DB2, and DB3. We will place each of these in a dedicated resource pool that we create. Let's begin with DB1. We will create resource pool 1 and assign DB1 to it. This is a lightly used database, so we will only assign it 8 CPUs, 32 gigabytes of RAM, and 500 gigabytes of disk space. And we will limit it to 128 IOPS. Let's move on to DB2. DB2 needs a little more power than DB1. So we create a resource pool, call it resource pool 2, and assign it 16 CPUs, 128 gigabytes of RAM, and 500 gigabytes of disk space. We will limit it to 1,000 IOPS. Finally, we have DB3. DB3 needs far more capacity than the other two. We create resource pool 3 and assign it 32 CPUs, 512 gigabytes of RAM, and 5 terabytes of disk space. And we also will limit it to 10,000 IOPS. Our excess capacity over here to the right is 8 CPUs, 328 gigabytes of RAM, and 4 terabytes of disk space. Our new multi-tenant database has isolated the 3 databases from one another. This means that once a database reaches its limit, it cannot obtain resources from the others. That's important. This will be great in the beginning, but over the course of time, 2 problems may appear. Problem 1. Each system is restricted to a fixed resource pool, and when the system load changes, its resources are still limited to its own resource pool, resulting in the inability to quickly expand resources and possibly resource waste. For example, in the above scenario, if our DB2 suddenly experiences a heavy workload during an activity, I hope to allocate more CPU and IOPS to it so that it can smoothly handle the peak load. Unfortunately, DB2 can only use the CPU and storage resources in its own resource pool, which is in this case resource pool 1. This causes me to be unable to supplement computing power and storage capacity for tenants according to their needs. Another example. Assume DB3 no longer requires the computing power and storage capacity in resource pool 3. The CPU and I/O capabilities in the sub-resource pool can be freed up for use by other tenants, such as temporarily helping DB2 handle peak traffic. Due to the inflexible resource pool settings, we're still unable to meet this simple resource scheduling requirement. Problem 2. In order for the database to accommodate new tenants or temporary peak loads of certain systems mentioned earlier, we must reserve a portion of the idle CPU and I/O processing capacity in the parent resource pool. When a new tenant joins, we can allocate a sub-resource pool for them to ensure their operation. However, It should be noted that many new systems are not immediately put into production when they do go online, or they do require fewer resources in the beginning. If we can allocate idle resources from other systems to it, or simply not allocate resources to it, could we save computing power and storage capacity? Next, we will look at TiDB resource control. When we consolidate multiple single-tenant databases into a single TiDB cluster, we don't need to plan how big each tenant's resource pool should be. Instead, we will use resource groups to manage how much CPU, RAM, disk, and IOPS a user can access. A TiDB resource group is a logical concept that can be thought of as a set of database users, sessions, and SQL statements, which we refer to as database users. So in other words, we refer to all these as database users. An important feature of resource groups is resource quotas, which represent the investment in CPU time, IO bandwidth, and IOPS and other indicators per unit database time. Each database user, and that is database user, session, SQL statement, can only use database resources within the quota assigned to the resource group it is bound to. With resource groups, we can control resources from the perspective of database users. For example, in the figure, the tenant DB1 database has just gone online and is in the test phase, so it doesn't require many resources. Therefore, we can bind DB1's users to resource group 1, which has low resource quota. Database 2 is online and under moderate load. The TiDB administrators bind database 2's user to resource group 2. Notice that resource group 2 is assigned medium quota. And you'll recall that DB3 is very busy. So the DBAs bind its users to resource group 3. This resource group is assigned maximum quota. Resource group 3's users have greater priority in resource usage even in the event of contention. So in summary, this resource management method based on resource groups achieves resource isolation from the perspective of database users, and it targets actual users, sessions, and SQL statements. This adds up to something very nice. We don't have to worry about how much each tenant's resource pool is allocated before we consolidate the databases. Next, let's consider change. I guess I need to be more specific. I mean changes in the way that our tenants are being used. Take the DB2 database, for example. Let's assume DB2 has experienced a significant increase in priority over time with an increase in load and concurrent access. In other words, it's a lot busier than it used to be. On the other hand, DB3 is now entering a period of reduced load and reduced concurrency. It no longer needs the resources allocated to it. Then, just to make this interesting, we migrate a new environment to our TiDB cluster, DB4. This tenant is not currently in use. If we manage resources through resource pools, we will need to reallocate resources for DB2 and DB3. This could result in downtime. Allocating resources for DB4, despite it being unused, would also be a waste. With resource groups, we can bind the users of DB2 to the resource group 3, which has a higher priority in resource allocation and a larger resource quota. For DB3 users, we can bind them to resource group 2 with the medium resource quota, so that the tenant's database does not need any adjustments. As for DB4, nobody uses it, so we don't need to consider its resource allocation at all. In this way, we allocate more for those who need it and less for those who need less. Now let's look at a scenario where the load on our cluster suddenly changes. In the beginning, database D2 has 2 users and a single resource group, 2. This resource group is assigned a medium resource quota. We know this because the priority equal option is set to medium. Imagine you get a Slack message warning us that a new product is launching tomorrow. This product will use DB2. While we appreciate the warning, it would have been very nice to have more than a day notice. So this application, denoted by user 3, will require several times more database resources than usual to handle the increase in load. Other services continue to run as usual. If we use a resource pool to increase the CPU and I/O capability of DB2, the services that previously did not require resource expansion will gain access to the newly added resources. Using a resource group, we only need to bind the relevant database users to the new resource group with larger resource quotas. Other users remain bound to the previous resource groups. In this way, we've expanded resources for those services that temporarily require more resource allocations. As shown in the diagram, we bind user 3 to resource group 3 with higher resource allocation quota. Let's return to our original diagram. Well, almost our original diagram. There's a slight but important difference. What happens if user 2 suddenly experiences a heavier load? Increases in database loads can occur due to events such as traffic switching or failover. So user 2 is bound to a resource group that is designed to accommodate normal database use. Fortunately, we can add a burstable option to this resource group. If burstable is enabled, the resource allocation quota of a resource group can be exceeded. This allows TiDB's free resources to be assigned to users who are experiencing atypically high use. Well, let's bring user 3 back into the picture. Recall that user 3 is a consistently heavy resource user, and user 2 is a sporadically heavy resource user. Using separate resource groups, including one with burstable set, provides us with a clever way of handling these types of situations. We've been focused on users, but remember, we can bind an SQL query to a resource group too. So take a look at the left-hand side of the diagram. We have lightweight query 1 that runs on DB1. It's an easy query that isn't resource intensive. We've assigned it to resource group 4. Notice the priority is set to low. Scanning to the right, we have resource intensive query 1 assigned to resource group 5. The priority is set to medium, and this query runs against DB2. Finally, we have resource intensive query 2, which has fire, which means it's really resource intensive. This query is bound to resource group 6. This resource group is the beefiest. The priority is high and burstable is set, which means that it can continue to exceed that for short periods of time.
If you want to learn more, scan this barcode and then you can get access to more PinCap training and certification resources.